Hello everyone, welcome for today's session. It's been a very long gap with respect to our previous session. No problem, we'll just have a quick revision of with respect to previous session and then we will continue with today's session. So in the last session we are talking about the reactance. What is actually the reactance is? So reactance is nothing but the opposition presented by either an inductor or a capacitor to an alternating current is called the reactance of the circuit. It means how a capacitor and inductor behaves when it is applied with an AC signal. Means how is the opposition it offers to the alternating current. So that is called as the reactance. That is faced by or represented by inductor and capacitor. So for inductor, we can write the reactance as XL is equal to 2 pi F into L. And for capacitance, the reactance is represented as X is equal to 1 by 2 pi F into C. So here in the capacitance, the frequency is inversely proportional to the reactance of the capacitance. As the frequency increases, the reactance decreases. Whereas in case of inductor, it is directly proportional. As the frequency increases, the reactance increases. And what is this impedance? Impedance is nothing but the total sum of these inductive, that is the reactive elements, is called the impedance. So the formal definition of impedance is the total amount of opposition. It is the total amount of opposition faced by an alternating current in an AC circuit consisting of resistive equivalent to the resistance in DC circuit. It means if we have a circuit where we have the resistor, inductor, and capacitor, and the way it is connected, maybe it is connected in parallel, maybe it is connected in series, then the type of the opposition it gives for the alternating current, so that is called the overall reactance. We call it as an impedance of the circuit. So I'd like to take to the view of the sides here. So yeah, so here we have to understand few things. Hope the screen is visible to you all.
Yes, sir.
Yes, thank you. So here we will discuss few points about the phase. Phase is in an AC circuit containing a resistive, if there is only a resistance, then whenever we applied an voltage and current, both are in phase. So it means this is an AC voltage source. Let us call it as VI, and here we have a resistor. And when we apply like this, so here what do we have? An voltage source means it has an voltage, and along with that it has a current also. Okay, so this red line you can call it as current, and this black variation you can call it as voltage. And when it passes through the resistor, then the phase shift, there is no phase shift at all. It remains to be same, means the current and this will remain to be in phase. There is no change in the phase. But if you see here in an AC circuit containing an inductor, for example, if it has an inductor, then the current will lag the voltage by an angle of 90 degree. So it means if we take a circuit here, sorry, I take it in terms of black. So this is an voltage source here. Now we have only an inductor in the circuit and nothing else. If it is connected like this, so here we have an voltage like this, and the current is also in phase like this. There is no change in phase. But what happens in the output? It means when it passes through the inductor, then if this is the voltage, then current will lag it by 90 degree. Something like this we will get. So this is the current and this is the voltage. So it means the current and voltage is in lag by 90. Means the current lags by 90 degree. It means the current is shifted minus 90 degree. That is what happens in the inductance. Okay. Okay, so if you can see in an AC circuit containing an inductance only, the current lags the voltage by an angle of 90 degree, but the power consumed will be zero. Now, if we have the resistance and inductance, what will happen? If we have both resistance and inductance, okay, just hold on. I'll just post the link. Somebody was asking it. Where I was, yeah, yes. Now what happens? Now let us take another circuit here. Now, in this case, what happens is that we have a resistor, we have an inductor, we have an AC voltage source. Then, in this AC voltage source, you can call it as anything. This is R and this is inductance L, inductor L. Now, when it passes through, so we have seen that when we apply an AC signal or AC voltage source or AC signal source across a resistor, there is no phase change in the voltage or current. But when it passes through an inductor, there is a phase change in current. Means the current will lag, will delayed by 90-degree phase. Okay, so same thing will be experienced here also. So across the output, so this is, if we call it as an voltage, then the current will be 90-degree in phase. So this shift will be minus 90-degree. Okay, so this will be minus 90-degree, and the power that is dropped, or the total resistive force, is now it is a vector sum of in react resistance and the inductance. So if you look into the total resistive force, now it is the vector sum of resistance and inductive reactance. So that will give the impedance. So here the impedance, we'll call it as Z. So here the impedance is nothing but it is a square root of, it is R square plus it is XL square. We can write. So this is the mathematical way of representing the impedance. So impedance is represented by Z. Now similarly, if we have a resistor and a capacitor only, these two components, and we apply to an AC source, this is R, this is C. Now what happens in this case is that, okay, we have not seen that case. Okay, let us see the case of first capacitance. Now if we have only a capacitive element, then what happens? The current leads the voltage by an angle of 90-degree. Okay, let me just have the capacitance here. Now when we have the capacitance, so what happens is that if this is the voltage, then whenever this AC signal pass through this inductor, so I'll get this. So what happens? This is current I and this is the voltage V. So now the phase shift will be plus 90-degree. It means the current is shifted by plus 90-degree for the capacitance. Okay, so this is how it behaves in an AC circuit. So capacitance, the current across the capacitance will be leading or shifted plus 90 degree with respect to the voltage. And when we have the resistance and capacitance, which is connected to an AC circuit, then the similar effect is applicable. There is no change because what happens is that across the resistance there is no phase change, only across the capacitance there is a phase change. So we will get here. So this is, if this is an voltage waveform, then the current waveform will be like this. So this is I and this is V, and the current will be phase shifted by plus 90 degree. I hope this point is clear for everyone. Any doubts so far? So it is very clear. For inductance, the current will be shifted by minus 90 degree, and for capacitance, the current will be shifted by plus 90 degree with respect to the voltage. All right. Now we will continue our discussion. Yes, anybody has any queries? Somebody's mic is unmuted. Okay. Now we will continue further. There is something called the resonance circuit, or a tuned circuit we can call. So this tuned circuit can be a combination of in any form. It can be a parallel connection or it can be a series tuned circuit. So let me write here. So there is something called the tuned circuit. The tuned circuit means, so there are two types. One is the series tuned circuit, and the second one is the parallel tuned circuit. Now whatever we have studied here, now we will going to apply that in a circuit in a series fashion and in a parallel fashion, and then we will see how does it respond and what is the behavior. So for that, I go here. So what happens is that we have seen here before, the inductance is directly proportional. The reactance of the inductance is directly proportional to the frequency, whereas the capacitive reactance is inversely proportional to the frequency. Now, if you write both of these graphs onto the single graph, and this is the capacitance, sorry, this is the capacitance, and this is the inductance. So this is the point where it meets. So it means this is the point where the XL is equal to XC. So that is called the resonant frequency point. If this x-axis is frequency, then this is the resonant frequency point F naught, and this is the we can call it as the reactance. The reactance we can call here. So this is the point where the XL is equal to XC. Okay, that is called the resonant frequency point. So if we talk about the series resonating circuit, RLC circuit, so if you write here, we have a circuit which has a resistor in series with an inductor and with a capacitor, which is connected to an AC signal. This is R, L, and C. Now we have both the inductor and capacitor, whereas in the previous discussion we have taken it separately. We have only inductor, we have only capacitor. Now the phase shift in the current and voltage, we have to observe it very properly. Now if this is the case, then what happens is that, So at this tuned point, so we know that the inductive reactance is XL is equal to 2 pi FL and X is equal to 1 by 2 pi into FC. So if the value of the inductance is greater than XC, then the circuit is called as inductive circuit. If the value of XC is greater than XL, then the circuit is called as the capacitive circuit. And the total circuit reactance is given by, it is a difference of XL minus XC. So we can write it here. This is the total reactance is, it is XL minus XC, or it can be XC minus XL, depends upon whichever is greater. It is not necessary that only it is inductance minus the reactance resistance. And then the total impedance, here it is given as you can see here, that is the R square plus XT square. So this will give the total impedance for a series circuit. Now, as I told you that if you plot a graph for a series resonance circuit, that is the inductive and the capacitive on the same graph, then it will both the graph will meet at one point. So that is called the series resonance point here. So in this series resonance point, so this is the point where XL is equal to XC, and below this it is a capacitive because XC is greater. If you see here, this is the point where the reactance of the capacitance is higher, whereas the reactance of the inductance is less. So below this point, it is a capacitive reactance circuit, and above this, it is an inductive reactance circuit. This is the point where it is only resistive circuit, where the capacitance and inductance effect will be zero because it's going to cancel each other. So then, what is the equation that we get is that we already defined in the previous session, I think. So XL is equal to XC. So it means it is 2 pi FL, which is equal to 1 by 2 pi into FC. Then when we take this will become F square. It is equal to 1 by 4 pi square into L into C. Then F is equal to, we will get a frequency of, let us call this as F naught. It is 2 pi into square root of L into C. So this is the equation. So using this equation, we can calculate what is it. Means based on the value of inductance in the capacitance or inductor or capacitor, we can find out what is this resonance frequency. So this is what the impedance chart that we will get. So at this point, at the resonance point, the impedance will be minimum. Okay, so if we draw the graph here with respect to the frequency, so here we have to note one thing. So we will get a graph like this. So this is the F naught point. So this is the impedance, and this is the frequency F. What happens is that this is the point where its impedance is very, very low. Why it is very low? It is because that it is only the resistance which is there in the circuit, because the inductance and the capacitance cancels each other. So I'll get this minimum. So impedance point is minimum. So whenever this impedance is minimum, if we draw a current chart, so at this particular frequency, the current will be maximum. Okay, this is the current I with respect to the frequency. So same F naught frequency, what happens is that the current is maximum. So we can conclude that, not parallel, sorry. In a series resonant circuit, at XL is equal to XC, whenever the XL is equal to XC, then its impedance is minimum, and the current at the resonance is maximum. So this type of circuit, we call it as an acceptor circuit. So this type of circuit is called as acceptor circuit, where when all the three elements are in series and at one particular point the XL is equal to XC, when XL is equal to XC, the impedance will be lower, means minimum at one particular frequency, and that is the point where the current is maximum. So the impedance of this series resonance circuit is minimum and the current at the resonance is maximum, and this circuit is called as acceptor circuit. So as you can see here, this is only, now what is the impedance left is the resistive value. Okay, so you see here the inductance and capacitance, it is like acts like a short circuit at that particular frequency. Now we have only the resistor. Now this is the current chart that we will get, what I had written before. So that is I is equal to V by R. So it depends on the voltage and whatever the resistance value. If smaller the resistance value, this peak will be very sharp. So this is also very important, which plays a very important role in bandwidth. So bandwidth, we normally take it as minus 3 dB. So if this is minus 3 dB, so then this is our bandwidth. So if I call this is F1 and F2, then bandwidth is defined as it is F2 minus F1. And this depends on the value of R. If the value of R is very low, then we will have a very sharp peak. It means we'll get a very sharp peak like this. Then the bandwidth, what we get is very narrow. Okay, it's supposed to be a dotted line. See, the bandwidth is very narrow. Now, if the resistance value is very high, then what we get is that the overall current will be less, but we'll get a peak something like this. So minus 3 dB we'll get here. So we'll get a wider bandwidth. So this is F1, this is F2. So why? Because I is equal to V by R. As the value of resistance increases, definitely the peak current value will be reduced, but we'll get a wider bandwidth. So it means the more frequency, it will allow more frequency. The purpose of this tuned circuit is used in filters, oscillators. There are many applications of this tuned circuit. So that is why we are talking about this tuned circuit here. So mainly it is for filters, you can think of, or noise cancellations. So similarly, now if you see the phase angle across the inductor and capacitor. So this is the point, the resonance frequency point, and below that it is the capacitive. So at the capacitive, what happens? The current is leading by 90 degree, and beyond this point, there is FR, the current is lagging by 90 degree. So this is the graph which you can see here, just for understanding. So remaining things I'll just skip about the Q point. Well, that will make it a little complex for you. It defines the quality factor. Okay. Let us quickly have a look at the parallel resonance circuit. Now we will see if these inductor and capacitor are, if they are connected in parallel. Now this is a resistor, and now this is an inductor and capacitor if they are in parallel. And we apply it to an AC signal. So this is R, L, and C. Now this is called as, parallel resonance circuit. Parallel resonance circuit. It doesn't matter whether the resistor is in series or parallel, because it has no effect on this overall resistance. It's okay. Even if we consider the resistance in parallel, we can consider this as, instead of R, we can consider as the conductance, that is 1 by R. Now again here at some point XL is equal to XC. We will get the same formula. The cutoff frequency, the resonance frequency will be 1 by 2 pi into root of LC. Now if you see at this point, what happens? So XT, that is the total reactance at this point. Okay. I have to write this in parallel. Otherwise, if it acts like an open circuit, then there is no path for the current to flow. So let me take the resistance in parallel. I'll connect this here. It's fine. So at the resonance condition, what happens is that the inductance and capacitance acts like an open circuit. And then here in the parallel resonance circuit, the impedance will be maximum. So in parallel circuit, what happens is that we'll get this curve. This is the frequency F, and this is the impedance. That is nothing but Z. And this is the resonance frequency F0. So whereas in this case, if you see, it is the bell curve. The bell is minimum is at down, and here the bell curve with a maximum point here on the top. So this is the resonance chart, the parallel resonance. Now below this, if you see, this is, you can see it as an increasing. That is why it is an inductive. It is an inductive circuit, and beyond this point it is decreasing. It is a capacitive circuit. So where the XL is greater than XC, and here the XC is greater than XL. Now this is the resonance point. So now for this case, we will get like this. So we will get the factor like this, and this is a point. So this is the total susceptance. So here the current is minimum in the parallel resonance circuit. So if you write with respect to this here, so we will get like this. So if this is the current chart, this is I, and this is F, and this is the resonance frequency F0. So we can conclude that with a parallel resonance circuit, the impedance of the parallel resonance circuit, is maximum, and the current through the current at resonance is minimum. That is why it is called as the rejector circuit. It is called as the rejector circuit. Okay. So this is about the tuned circuit. So we have the two types of tuned circuits. So one is a series resonance circuit, where in the series resonance circuit, at resonance, the impedance is minimum and the current is maximum. And this is a parallel resonance circuit where all the elements are connected in parallel. And we have at this point, the impedance is maximum at resonance and current is minimum at resonance. It is called as the rejector circuit. Now I'll move on to the next topic. Amplifiers I had been talked in the previous session also. Now let us talk about the different types of amplifiers. So type in the sense, actually I'm talking about the classification of amplifiers. If I call the type, then it will be a mistake. because type means there will be an voltage amplifier or power amplifier and so on. Specifically, I supposed to talk about the classes of amplifier. So there are different types. Sorry, again, I'm using this word called type. So it's supposed to be the classes of amplifiers. So the different types, the different class of amplifiers. So that is called as the class A amplifier, class B amplifier, and class C amplifier. And there is also called class AB amplifier. And there are different versions. We'll just talk a little bit about these three types of class of amplifiers. So what do we mean by class amplifiers? Class of amplifiers. So it means if this is my amplifier circuit, if this is an amplifier, if I'm applying some input here, because basically for an amplifier we'll apply this analog signal itself or a sinusoidal signal, output should be the magnified version or the amplified version of the input. But here the question is that, do I need to have across the output the entire input or only the portion of the input is sufficient? So that defines the class amplifiers. The class amplifiers will give the output only with respect to the portion of the input waveform. So let us take the first one here. Class A amplifier. So to understand the class A amplifier, I'll just write a transconductance graph. So transconductance graph, it is like this. That is with respect to the input current and output voltage. Output voltage to the input current or something like that we can write. It's a transconductance. Now across this transconductance, let me extend this a little bit. Yes. Okay. This is the output voltage. Now if this is the input which I'll apply here, then with respect to that, so this is a reference line here. So here I will be applying the input. So this you can consider as the input, and these points are the output. So you will get the entire signal like this. Okay. So this is the input and this is the output, and this is the point which is chosen here with respect to this, wherever whatever the signal is applied. So you'll get the entire signal across the output. This is called as the the class A amplifier. So class B amplifier means, let us write here a similar kind of graph. And now we have a transconductance line here. And now with respect to this, what happens is that we will be selecting the point here and we are applying the input. Okay, let me not write here. So I'm going to be half peak. Where can I get? where we can select here itself. And with respect to this, if I apply, let me have this. Like this. Now, this is the point. Now what happens here is that if you see, so now this is the line, and this line and this line is coincide. So what do I get here across the output is only this. Means only this portion. That is this. So only half of the wave I am getting across the output. So this is called as, if we get an output like this from an amplifier, so it is called as the class B amplifier. Okay, exactly the half peak. Now let us talk about the next type of next class of amplifier. Sorry, that is class C amplifier. So let me write the transconductance graph once again. Be a little bit of linear rather than exponential. Okay. Now I'll select the point somewhere here, and you will be having this point. Now this is the point. Now here what happened is that we get this. It means we got this much of signal across. Sorry, my mistake. It's not that. Let me erase this completely. It is only the part of half wave. It is not beyond half wave. I'll just erase this. So if I take this point here, and if this is the input, and what happens is that, so this is the point. So this is the point. So here we got this portion of signal here. So it means we are getting only the small portion of signal across the positive peak. Previously in class B, we got the entire positive peak, and in class C, we will get only the part of the positive peak, or maybe the negative peak. That is called as class C amplifier. So the different types of class of amplifiers, that is class A, class B, class C, class AB, that depends on what type of output waveform we want. We can choose this because that will save a lot of power. The amplifier, because amplifier requires a lot of power to amplify the signal. So whether we want to amplify the entire signal, positive peak as well as negative peak, or only positive peak or portion of positive peak, we can make a wise decision so that we can reduce the power consumed by an amplifier. So that's it. Next, we'll move on to the communication topic. So today I'll give just an introduction to the communication topic, and in the next session we'll be talking about the super heterodyne receiver, and then further communication topics about modulations and all those things we'll be talking in the next session. So we're talking about the communication. As you all know, the initial communication, the wireless communication started by transmitting the Morse code by Samuel Morse across the Atlantic Ocean. So the frequencies, whatever we talk, it is categorized as audio frequency and radio frequency. So audio frequency, basically it range from say 20 hertz to 20 kilohertz. Some textbooks says it is 10 hertz to 10 kilohertz is the audio. Okay, that is audio frequency range. Audio frequencies we can consider as 20 hertz to 20 kilohertz, and beyond this, it is from 500 kilohertz and above. We call it as the radio frequency signals. So let us have a look at the table of the frequency categorization, and then we'll talk about the simple transmitter and the receiver. So we can make 3 columns, that is 0.5 megahertz to 3 megahertz. It is called as low frequency, LF. Then 3 megahertz to 30 megahertz, we call it as HF or high frequency. Let us call this as HF. Then 30 megahertz to 300 megahertz is called as very high frequency. It is called as VHF. This frequency range, as you are going to be all hams, you should be very well aware of these categories of low frequency and high frequency. What is the range that it comes? Because when we talk about say 10 megahertz, what is it? 10 megahertz is a low frequency, high frequency, or it falls under very high frequency. So 10 megahertz falls under high frequency range. So then 300 megahertz to 3000 megahertz, or this is also called as 3 gigahertz. So this is ultra high frequency, which is UHF. And then 3 gigahertz to 30 gigahertz, it is super high frequency, SHF. And 30 gigahertz to 300 gigahertz, it is extra high frequency. It is EHF. Okay, so at least you should remember these 4 categories. So 0.5 megahertz, it is nothing but it is 500 kilohertz. So from 500 kilohertz to 3 megahertz, it is low frequency. And 3 megahertz to 30 megahertz, it is high frequency. And 30 megahertz to 300 megahertz, very high frequency. And 300 megahertz to 3 gigahertz, ultra high frequency. And 3 gigahertz to 30 gigahertz, super high frequency. And 30 gigahertz to 300 gigahertz, it is extra high frequency. So now let us take a simple transmitter and a receiver setup. This is for CW transmission. CW means it is continuous wave transmission. It means the dot and dash transmission, the Morse code transmission. For this, for example, I want to transmit in high frequency. Then what do I need is that I need a high frequency oscillator. So I'll just take a high frequency oscillator. Then we will take an amplifier, because we will amplify the signal before transmitting, and we will take an antenna of suitable whatever frequency is there. We will design the antenna with respect to that, and we will transmit. Suppose I am transmitting this Morse code or CW transmission at 7 megahertz. I transmit. Then at some point, some user has to receive this. So what should be the receiver setup? So receiver should have, we cannot directly give this to a speaker by an antenna. Okay. If we give this to speaker, or maybe we can amplify and give this to speaker, and what happens is that the 7 megahertz is not an audio range. It is not an audio range, 7 megahertz, because our ears can recognize the frequencies from, say, 20 hertz to 20 kilohertz, but practically it is up to, say, maybe up to 5 kilohertz, and maximum up to 10 kilohertz. But audio range, we will say it as 20 to 20 kilohertz. So even if we give to speaker, even if speaker plays this sound, we cannot able to hear it, because our ears cannot recognize that. So what do we need to do is that we need to have a simple conversion. So for the conversion, we need a mixer circuit. From antenna, we will receive the signal, we will provide to mixer, and mixer will have the two inputs: an oscillator this one. Now I have to convert the signal to 7 megahertz. I have to convert this to 1 kilohertz. So what should I do? So this local oscillator, whatever it is there, this should have the frequency of 7 megahertz plus 1 kilohertz. So it means this oscillator should generate a 7 point. Just hold on. Here's the calculator. It is 7 megahertz plus 1 kilohertz. So it means this oscillator should generate 7.001 megahertz of frequency. Okay, 7.001 megahertz of frequency. And now here we are getting 7 megahertz. Here this is giving 7.001 megahertz. So what happens is that there are two possibilities. That is 7 megahertz plus 7.001 megahertz. We will get 14.001 megahertz as the output. And second possibility is that 7 megahertz minus 7.001 megahertz, we will get 1 kilohertz. So this is not required, so we'll neglect. So we will take the difference. So when we take the difference, here the output we will get 1 kilohertz, and that I'll give it to an amplifier, an audio amplifier. An audio amplifier, and from that audio amplifier I will give it to speaker. Then we can hear that whatever the transmitted signal will receive at this point. Okay, so before concluding today's session, I'd like to introduce one more topic, that is VFO, variable frequency oscillator. It is called as VFO. So variable frequency oscillator can able to generate the different frequencies which are required for the transmission. So basically an oscillator can generate in terms of multiple harmonics. Okay, so an oscillator will have one fundamental frequency, and there will be certain harmonic frequency. So this might be a first harmonic, then second harmonic frequency, and third harmonic, and so on. So it means, just let's understand that as a fundamental frequency, if the fundamental frequency is 3.5 megahertz, if this is the fundamental frequency, then we can have the first harmonic at 3.5 into 1, which is equal to 3.5 megahertz itself. That is, the first harmonic is nothing but the fundamental frequency itself. And the second harmonic will have 3.5 into 2, which is equal to 7 megahertz. And the fourth harmonic, third harmonic we will not discuss because that is not of our concern. So 3.5 into 4, we will get 14 megahertz. So third harmonic we will get 10.5 megahertz, which is not of interest. Then sixth harmonic, it is the multiple of 6, we will get 21 megahertz. And the eighth harmonic is 3.5 into 8, we will get 28 megahertz. Why we are talking only these frequencies? Because in ham radio, we are supposed to transmit in these frequencies in HF range. Okay, so 3.5 megahertz, 7 megahertz, 14 megahertz, 21 megahertz, and 28 megahertz. It means if 3.5 megahertz is the fundamental frequency, then its first harmonic will be the same. We'll be taking its second harmonic, fourth harmonic, sixth harmonic, and eighth harmonic. It means we can use the oscillator and we can tune to one of the particular harmonics, and we can use that frequency to transmit our CW signal. Okay, and that kind of oscillator is called as the variable frequency oscillator. So the block diagram and the other things we will see in the next session. So if you have any queries, you can ask. Otherwise, we will wind up our today's session. So any queries, kindly you can ask.